This lesson introduces enterprise rack visually. The goal is to understand what Docker, PostgreSQL, pgvector, embeddings, transactions, and connection pools each contribute. The system should not answer only from a model's memory, it should first find relevant company evidence. Here, the question leads to the password reset policy, and the answer uses that policy. This is the central purpose of RAG. RAG means retrieval augmented generation. Retrieval happens first, the system finds useful passages. Generation happens second. The language model writes using those passages. This separation matters because retrieval quality can be tested independently from writing quality. Docker runs the packaged environment. PostgreSQL organizes and protects the data, while pgvector is an extension inside PostgreSQL that adds vector storage, distance operators, and vector indexes. They're related, but they're not interchangeable. A Docker container is an isolated running package. It contains PostgreSQL and pgvector. Port 5432 here is the connection door used by the application. Docker makes local development repeatable, but it does not by itself provide production high availability. Here we have embedding. An embedding model converts text into a vector, which is a list of number. Think of it as coordinates on a meaning map. In the next slide, we will see the example of a meaning map. Related text should receive nearby coordinates. The three number vector shown here is only a teaching example. Real models usually create much larger vectors. Here we have the visual example. Each dot represents a piece of text. Password passages clustered together. VPN and expense passages form other clusters. The question lands nearest to the password cluster. Real vector spaces actually have many dimensions, but pgvector can calculate those distances even when we cannot draw them. The embedding model creates numbers. PostgreSQL and pgvector store and compare those numbers. pgvector does not understand raw text by itself and does not create embeddings. Documents and questions must use the same compatible embedding model. So, what is a document then? A document is the complete source, but a chunk is a smaller passage derived from the document. Searching chunks is more precise than searching whole manuals. Document level information stays in the documents table, while searchable passages and embeddings stay in the chunks table. The document primary key uniquely identifies one source. Then each chunk contains that document ID as a foreign key. PostgreSQL checks the connection and rejects chunks that point to no document. This way, it will keep citation and deletion behavior reliable because there are no orphan chunks. All the chunk all the chunks must be pointed back to the document. When a question is embedded, like when a user typed in the question, it will be embedded and then searched and returned as evidence. The language model receives the selected passage and source ID and then writes the answer. So the language model should not receive direct, like it should not access direct database, but instead, the retrieval actually sent the relevant information to the LLM to write the answer. And ingestion uses a transaction as well. Ingestion actually begins when we want to extract, and then like do the chunk and embedding stuff. The system of ingestion will insert the document, inserts all chunks, marks the document ready, and commits. If any database step fails, rollback removes the transaction's earlier writes. This is very important because the rollback will prevent users from getting half of a document. So if if the document or the chunks don't work, then it will do the rollback. pgvector compares the question vector with stored each chunk vectors. Each comparison produces a distance as a number shown on the screen. The system sorts from the smallest distance to the largest. Here, the password policy ranks first because the question was about the password. Distance is useful for ordering. It is not automatically a confidence percentage, but it of course helps. And then let's talk about vector search. Vector search handles related meaning even when wording changes. Meanwhile, keyword search handles exact IDs, names, and error codes. Enterprise RAG often combines both candidate lists, optionally relinks them, and selects the best evidence. Opening a new PostgreSQL connection for every request wastes resources and can exhaust the connection limit. However, in the real rack production, the users are usually more than one person at a time, and that's what we call concurrent users. In order to handle and support concurrent users, we usually use something called pool. So a pool keeps about a set of reusable connections. Requests borrow one briefly and return it. So extra requests wait instead of like creating unlimited sessions. This is very important when it comes to real rack production. And then we have implementation. Implementation can be remembered as 6 steps. This is like the overview of how to implement RAG in the real enterprise use. So we start with the database and then create documents and chunks, generate embeddings, retrieve the nearest passages when a question was put in, and add a bounded connection pool. We also have transactions. Transactions and permissions protect the workflow because, as we said earlier, that transactions ensure rollback can happen. So the unfinished chunks won't be sent to the answer. So this slide preserves the implementation path without failing like the lesson with code. Not yet, but you can actually see the code for starter in the description. Usually the local demo, like the first prototype, teaches the system shape, but when it comes to production needs to add authentication, document permissions, TLS or transport layer security, secret management, backups, restore testing, failover monitoring, and retrieval evaluation, stuff like that. Docker Compose makes local setup repeatable. Remember the boundaries. The embedding model creates vectors. PostgreSQL organizes evidence. pgvector compares vectors. The language model writes from the retrieved evidence. A trustworthy system retrieves the best authorized evidence, protects access, and measures quality.